backlash against CEO Elon Musk's political positions.
Sales are down 50% year over year. China's sales were down 50%.
In the last couple months, the stock's just been obliterated.
For decades, the world's biggest car companies believed they had electric motors completely figured out.
Since 2015, he said that every year, next year. We're now in 2025, and there's not one car on the road from Elon Musk that can do that.
They had the factories, the deep pockets, and over 100 years of experience.
While Musk was promising fully autonomous rentable Teslas, the company was transforming itself into a high-volume electric car maker.
Then Tesla showed up with a brand new motor technology that broke the old rules.
How we're doing on popularity? Well, we actually literally make the best-selling car on Earth of any kind.
And left the entire industry in stunned silence. Rival engineers didn't respond with bold counter-announcements or flashy prototypes. They just went totally silent. So, what did Tesla actually build that left the whole industry speechless? And why is everyone else still scrambling to catch up? Join us as we break down the carbon-sleeved motor technology that's forcing competitors to rethink everything they thought they knew. The motor that broke the rules. To understand why Tesla's motor has competitors genuinely rattled, you first have to understand the common enemy that engineers have been fighting against for decades inside every electric motor ever built. And that enemy is something you can't see but can't escape. It's called centrifugal force. Inside every electric motor sits a spinning component called the rotor. This is the part that actually generates the motion that moves the car. And as the motor speeds up, the rotor spins faster and faster until the centrifugal forces acting on it become enormous. Those forces are always trying to push the rotor outward, to expand it, stretch it, and eventually pull it apart. So for years, engineers had a very simple rule. There was a ceiling on how fast a rotor could spin without destroying itself, and every motor ever built for a road car was designed to stay safely under that ceiling. Tesla decided to go through the ceiling instead, and what they came up with was both brilliantly simple in concept and brutally difficult to actually pull off. They wrapped the rotor in carbon fiber. Here is where it gets interesting, because this was not just any carbon fiber wrapping. Tesla had to build a machine from scratch to do it. Elon Musk explained this publicly during the Model S Plaid delivery event in June 2021 at Tesla's Fremont factory. He said that carbon and copper, the two main materials in this rotor, have very different rates of thermal expansion. When one heats up, it expands at a different rate than the other. So if you just wrap carbon fiber around the copper rotor and leave it, the differences in expansion over time and at high temperatures could cause the sleeve to loosen or fail. By replacing heavy steel or titanium rotor sleeves with carbon fiber, Tesla also eliminated the eddy currents, or parasitic electrical loops, that plague conventional high-speed motors. This material shift virtually cuts out hundreds of watts of heat loss, ensuring the rotor runs cooler while maintaining peak efficiency at extreme speeds. To solve that expansion dilemma, Tesla engineers had to wind the carbon fiber over the rotor under extremely high tension using a custom machine they designed and built themselves. No such machine existed before this. Tesla had to invent both the process and the equipment to carry it out. The result of that effort was a rotor held together under compression from the carbon sleeve, meaning the sleeve squeezes the rotor inward, counteracting the centrifugal forces trying to push it outward. And with that problem solved, the rotor could spin at speeds that would have torn apart every previous design. The two rear motors in the Tesla Model S Plaid can spin at up to 20,000 revolutions per minute. To put that in context, the previous generation of Tesla's high-performance motors topped out at around 18,000 revolutions per minute at 155 miles per hour. The Plaid motors pushed that to an estimated 23,308 revolutions per minute at 200 miles per hour, according to engineering analysis published by Inside EVs in June 2021 using Tesla's stated performance data. But raw RPM wasn't even the most important part of what changed. The real breakthrough was what happened to the power curve. Traditional electric motors reach a peak power output at a specific speed and then start to taper off. Power drops as you go faster. Every single motor works this way because at higher speeds, the magnetic field becomes harder to maintain efficiently. The Plaid motor, because the carbon sleeve holds the rotor so precisely even at those extreme speeds, maintains an almost flat power curve from low speed all the way up to the 200 miles per hour top speed. You get maximum power at 80 miles per hour. You still get maximum power at 160 miles per hour. There is no transmission, no gear change, and no fall-off. Just continuous, sustained power across the entire speed range. Then there's what this motor actually delivers in a car that 4 people can sit in. The Tesla Model S Plaid uses 3 of these permanent magnet synchronous reluctance motors, producing a combined 1,020 horsepower. It can go from 0 to 60 miles per hour in 1.99 seconds. It runs the quarter mile in 9.23 seconds at a trap speed of 155 miles per hour. It does all of that while still being a luxury sedan with a back seat, cup holders, and a 396-mile EPA-rated range. The motor itself, just the motor, weighs approximately 99 pounds. The complete drive unit, including the single-speed transmission and inverter, comes in at around 210 pounds. You can physically pick up this motor and carry it, and it can accelerate a 2-ton car to highway speed in under 2 seconds. Elon Musk called this motor arguably the most advanced motor on Earth outside of maybe a lab somewhere, in a Twitter post following the delivery event. He wasn't speaking loosely, he was describing a production motor, in a car you could buy off Tesla's website, that was performing at a level that engineers had previously only seen in purpose-built laboratory or racing environments. This was not a concept or a prototype. This motor went into production and was delivered to paying customers starting June 2021. But stay with us, because what happened when the world's best automotive engineers actually tore this thing apart is where the silence really began. What the teardown experts found and why it scared them. Sandy Munro is not a man who gets easily impressed. He runs Munro & Associates, a manufacturing analysis and teardown firm that has worked with almost every major automaker on the planet. His entire professional reputation is built on finding faults, on pulling vehicles apart bolt by bolt, and telling clients bluntly and publicly what is wrong with them. He is the person automakers fear hearing from because he is going to tell the truth, regardless of who is paying attention. When Munro and his team got hold of a Tesla Model S Plaid and started taking apart the motor assembly in early 2022, the criticism they were known for didn't come. What came instead was different. After removing the motor cover, Sandy Munro's on-camera reaction was, in his own word, "Whoa." And over the course of the Teardown series on his Munro Live channel, he described the Model S Plaid's engineering as to die for. His team called the battery pack an engineering masterpiece. So what did they actually find when they opened the motor up? The first thing that stood out was the carbon fiber rotor wrap itself. The pre-preg carbon sleeve holds the rotor in compression and eliminates the metal bridges that traditionally connect sections of the laminate stack around the magnets. Think of those bridges like a leaky pipe. They let energy escape before it can do any useful work. In conventional motors, those bridges are structural, but they also create what engineers call leakage flux, a path where magnetic energy bleeds away and gets wasted instead of doing useful work. Tesla removed those bridges entirely and let the carbon sleeve provide the structural function instead. The result is a cleaner, more efficient magnetic field. Tesla claimed internally that this redesign produced a 25% boost in torque and power, a claim backed by patents filed at the time. Munro's team also tested the magnet strength of the Plaid rotor against other motors they had torn down, including those from the Ford Mustang Mach-E and the BMW i3. Using a calibrated force gauge to measure how hard it was to pull the magnets free, the Plaid rotor required more force than any of the others. Tesla was using stronger magnetic materials than any of its main competitors. Then there was the inverter design. The same inverter circuit board is shared across the Model 3, the Model Y, and the Model S Plaid with only minimal chip-level modifications. This is a manufacturing decision with enormous financial implications. Instead of designing and tooling a unique inverter for each vehicle, Tesla standardized the component across its lineup. Fewer unique parts means simpler supply chains, lower inventory costs, faster production lines, and easier over-the-air software upgrades. Sandy Munro recognized this as genuinely clever lean manufacturing thinking rather than a corner cut. What Munro's team couldn't easily copy or reverse engineer was the manufacturing process itself. Knowing what the carbon sleeve does is one thing. Understanding exactly how Tesla winds that fiber at high tension using a custom-built proprietary machine without applying heat that could weaken the magnets is another thing entirely. That knowledge does not show up in a photograph of the finished part. It lives inside the company that spent years developing and refining the process. You can measure every dimension of the rotor. You can map the magnetic field. You can weigh the carbon sleeve. And you still don't know how to make it. This is the detail that made engineers at rival companies genuinely nervous. The physical part is impressive, but the manufacturing capability behind the physical part is what is truly hard to compete with. Elon Musk was clear about this when he said Tesla had to design the machine that makes the rotor, because no such machine existed anywhere else. That custom machine is sitting in Tesla's factory right now. And building a replica would take years of engineering work, tool development, and failed prototypes before anyone got close. It's also worth noting that Tesla's VP of Vehicle Engineering, Lars Moravy, confirmed in a podcast interview on Ride the Lightning in May 2026 that the company's plan for a future tri-motor Model 3 would also use carbon-sleeved rotor motors, meaning this technology is not staying exclusive to a $90,000 sedan. Tesla is planning to push it further down the lineup. And the next-generation drive unit that Tesla has been developing for its future vehicle platform takes the cost question to a completely different level. Tesla's target for the complete drive unit on its next-generation platform, motor, electronics, and gearbox together, is approximately $1,000. According to Wikipedia's sourced entry on the Tesla next-generation vehicle platform, that drive unit is also being designed with no rare earth minerals. Many competing drive systems cost 3 to 5 times that amount to produce. If Tesla hits that target even approximately, no legacy automaker can match it with their current cost structures. And the motor is only one layer of what Tesla has built. So stay tuned, because this is where the full picture comes together. And it's bigger than most people realize. The battery, the data, and the charging empire. The motor got everyone's attention, but the motor alone does not explain why competitors went quiet. To understand the full weight of what Tesla has built, you have to look at what surrounds that motor. The battery technology, the software systems, the real-world data flowing in from millions of vehicles every single day, and the charging infrastructure that every major automaker on Earth has now formally surrendered to. Starting with the battery. Tesla has been developing its 4680 battery cell since the company's Battery Day presentation in September 2020. The cell is named for its dimensions, 46 millimeters wide and 80 millimeters tall. It was designed from the ground up to change the economics of electric vehicle manufacturing. Compared to the 2170 cells Tesla used previously, the 4680 offers 5 times the energy capacity per cell, which means fewer cells are needed to build the same pack. Fewer cells means simpler thermal management, fewer connections, and a lighter, more compact overall design. Getting there has been hard. Tesla struggled for years with the manufacturing process, particularly a technique called dry electrode processing that eliminates the need for solvent-based coating steps and could significantly reduce cost and factory floor space. Elon Musk himself said at the 2025 annual shareholder meeting that pursuing that process at scale turned out to be way harder than the company originally anticipated. But by the end of 2024, Tesla's in-house 4680 cell production team at Gigafactory, Texas, had reached a landmark. Their cells became the lowest cost per kilowatt-hour battery cell that Tesla sources from any supplier, beating out established external suppliers, including Panasonic and LG Energy Solution. Michael Guilfoyle, Tesla's Giga Texas Director of Cell Manufacturing, publicly confirmed this milestone. By Tesla's Q4 2025 earnings call in January 2026, the company confirmed that both the anode and cathode of the 4680 cell are now being produced using the dry electrode process, meaning both halves of the cell are manufactured with the lower cost, lower energy technique. The dry electrode process is expected to push cost advantages another 30% further once fully ramped. The 4680 also serves a structural role in Tesla's vehicles. In cars like the Model Y built at Gigafactory Texas and Gigafactory Berlin, the battery pack is integrated directly into the vehicle's floor structure, removing a separate chassis layer and reducing weight and complexity. This is a design approach no competitor has replicated at production scale. Now add the data layer on top of the battery and the motor. Every Tesla on the road is equipped with cameras and sensors that are constantly processing driving information. And every mile driven by Tesla's fleet teaches the company's AI systems more about real road conditions than any controlled test environment ever could. As of February 2026, Tesla's full self-driving system has logged over 8.4 billion cumulative miles of supervised driving data. In 2025 alone, the fleet logged 4.25 billion miles. In just the first 50 days of 2026, Tesla owners added another 1 billion miles on top of that. Tesla currently has over 5 million vehicles on the road equipped with the hardware and software necessary for full self-driving. That fleet is estimated to generate roughly 50 billion miles of total driving data per year, which works out to around 100,000 miles per minute. A competitor starting an autonomous driving program today cannot buy 5 years of that data. They cannot manufacture it with simulations. They can only start collecting their own, which means they fall further behind every single day Tesla's fleet keeps growing. The competitive picture got even starker when General Motors quietly shut down its Cruise robo-taxi program following safety incidents and regulatory setbacks, leaving Tesla as the only American automaker with an active full autonomy roadmap and a deployed consumer product. In January 2026, Tesla had 1.1 million active full self-driving subscribers paying $99 per month, nearly twice as many as GM had for its competing Super Cruise system. And then there is the charging network, which is the most concrete example of how completely Tesla's position has changed the competitive landscape. Tesla built the supercharger network starting in 2012. For years, rivals dismissed it as a nice convenience feature for Tesla owners, not a strategic weapon. They were wrong. By the time the rest of the industry woke up to what had been built, Tesla's supercharger network had already achieved a 99.95% uptime rate and expanded to a point where superchargers made up 3 out of every 4 fast chargers in North America. What happened next is one of the most remarkable competitive surrenders in automotive history. In May 2023, Ford Motor Company became the first major automaker to announce it would abandon its own charging standard and adopt Tesla's connector, the North American charging standard, across its EV lineup starting with 2025 models. Ford's announcement triggered an industry-wide domino effect. Within the following months, General Motors, Rivian, Volvo, Polestar, Nissan, Mercedes-Benz, Hyundai, Kia, Genesis, Honda, Acura, Porsche, Audi, BMW, Toyota, Volkswagen, Subaru, Lucid, and Stellantis all announced plans to adopt NACS as well. SAE International, the Society of Automotive Engineers, formally standardized the NACS connector as the J3400 standard, meaning it is now the official charging connector of the electric vehicle industry in North America. A charging technology that Tesla developed and owned has become the industry-wide standard. Virtually every new EV sold in North America, beginning with the 2025 model year, uses Tesla's connector. And every time a non-Tesla EV owner plugs into a supercharger station, Tesla collects a charging fee. These are companies that have been engineering vehicles for over 100 years. And they looked at Tesla's charging network, looked at their own, and made the collective decision that the smart move was to join Tesla's infrastructure rather than compete with it. That is how far ahead the lead has grown. Why catching up is harder than it looks, and what comes next. There's a tempting way to look at what Tesla has done and think about it as a lead that can eventually be overcome. Competitors can study the motor. They can hire engineers. They can spend money. They can build their own batteries and their own charging networks. And over time, won't the gap narrow? That's the logical assumption. But the actual picture, when you look at it honestly and with updated data, is considerably more complicated than that. Start with the motor itself. The carbon-sleeved rotor is not a secret. The principle behind it is publicly documented. Elon Musk explained how it works at the delivery event and in tweets. Sandy Munro tore one apart on camera and walked through every component. Academic engineers and industry analysts have written detailed papers on electromagnetic design. Anyone in the world can read all of this. And yet, as of mid-2026, no competitor has put a carbon fiber sleeved rotor motor into a production vehicle at scale. The reason is not lack of knowledge. The reason is what Musk said when he pointed out that Tesla had to design the machine that makes the rotor. You can understand a process perfectly and still not be able to execute it. Building the proprietary winding machine, tuning the tension parameters, solving the thermal expansion problems between carbon and copper, achieving the consistency needed for millions of units rather than dozens, all of that takes years of engineering iteration that cannot be compressed by spending more money. You simply have to work through it. Then there is the battery situation. Tesla's 4680 team in Texas achieved lowest cost per kilowatt-hour status by the end of 2024 and confirmed full dry electrode manufacturing on both anode and cathode by early 2026. The technology roadmap includes 4 new 4680 variants under development, designated internally as NC05, NC20, NC30, and NC50, with 2 of them incorporating silicon-carbon anodes that can store more energy than standard graphite anodes and could deliver meaningful range increases without making the battery pack larger or heavier. Tesla is also working to eliminate rare earth minerals from its motor designs and reduce dependence on Chinese supply chains, which adds a geopolitical layer of independence to its technical advantages. The data advantage compounds every single day in a way that money alone cannot replicate. Tesla's FSD fleet logged 4.25 billion supervised miles in 2025 and was on pace to exceed 10 billion cumulative miles by mid-2026. Each of those miles contains video, sensor data, and driving behavior information that gets fed back into the training systems for Tesla's neural networks. Tesla replaced its earlier Dojo supercomputing initiative, which it shut down in August 2025, with a more practical approach. The company's Cortex AI training cluster at Gigafactory, Texas, is built on approximately 50,000 NVIDIA H100 GPUs, and by Q2 2025, had been expanded with an additional 16,000 H200 GPUs, bringing Cortex to a total of 67,000 H100 equivalent units. Accumulated AI-related capital expenditure had reached approximately $5 billion by early 2025. That computing infrastructure is being used to train the systems that power Tesla's full self-driving software. In June 2025, Tesla launched its robotaxi service in Austin, Texas, using Model 3 and Model Y vehicles operating without human safety drivers in some scenarios. Musk stated plans to expand the service to Dallas, Phoenix, and Miami in 2026. The Cybercab, a purpose-built autonomous vehicle with no steering wheel and no pedals, is targeted for volume production starting in 2026. Now look at where Tesla's main competitors actually stand and be honest about it. Ford built genuine electric vehicles with the Mustang Mach-E and the F-150 Lightning, and both generated real consumer interest. But Ford's EV division reported significant losses per vehicle over multiple years as the company tried to scale up production. Rivian attracted enormous investor enthusiasm and delivered impressive trucks, but its production costs remained high and profitability stayed out of reach for years. GM's Cruise robo-taxi program, once seen as a serious competitor to Tesla's autonomy ambitions, was shut down entirely after safety incidents and regulatory pushback in late 2023 and early 2024. Even Volkswagen hit repeated software and production delays on its MEB electric platform that caused years of setbacks across the ID family of vehicles. The only competitor that genuinely operates at comparable scale is BYD in China, which has matched and in some years exceeded Tesla's global delivery numbers and has achieved cost competitiveness through scale and strong government support. BYD does not yet compete at Tesla's level on software, autonomy, or charging infrastructure in Western markets, but it represents the most credible manufacturing challenge Tesla faces. What makes Tesla's position genuinely hard to challenge is that all of these advantages, the motor, the battery, the data, the charging network, and the autonomy software, are not separate things operating independently. They feed each other. A better motor in a more efficient vehicle gets better range. Better range makes the car more attractive. More attractive cars get bought. More vehicles on the road means more data flowing into the AI training systems. Smarter AI means better FSD. Better FSD means higher subscription revenue. Higher revenue funds more motor research, more battery development, and more supercharger expansion. The cycle keeps turning, and it has been turning for long enough that it has real momentum. A competitor looking at this picture from the outside isn't just trying to close a gap in one technology. They are trying to close a gap in 5 or 6 mutually reinforcing technologies simultaneously, while also building out a charging network, a data collection fleet, a software development organization, and a cost-efficient manufacturing operation. All at the same time. All against a company that has been building all of those capabilities in parallel for over a decade. That is the real reason rival engineers went quiet when they looked at the Model S Plaid motor. They weren't just looking at a rotor wrapped in carbon fiber. They were looking at evidence of everything that produced that rotor, and understanding the full weight of what that evidence meant. So, what do you think about all of this? Let us know in the comment section below. If you enjoyed watching this video, make sure to like, share, and subscribe to our channel for more. Also, click the next video shown on your screen. You will enjoy it.